This is House Planning Help episode 95. Hello, I'm Ben Adam Smith, and this is the podcast for you if you want to self-build or retrofit. I'm exploring what houses we should be building in the 21st century. My personal goal is to create an energy-efficient home before I turn 40 in August 2016. Coming up in this session, my guest is mechanical engineer Harold Orr as we look at the significance of the Saskatchewan Conservation House. And there's something very special when you do an interview with anyone who has a lifetime of experience. I've been fortunate enough to do this a few times in my career. And without fail, you always get a really interesting interview. So I hope that you're absorbed by this. It's slightly different to what we normally do because it's a bit more of the history. We're going back to the 70s. And I have a quick thank you to do. Monty Paulson from Red Door Energy Design in Vancouver, he suggested this interview to me. I always knew that Harold was a pioneer and that he'd make an interesting interview. But what he went on to say is he's got some great stories, some brilliant stories, because, of course, when you're a pioneer, you have to figure stuff that we take for granted out at that time. You're going to hear some of that in today's interview. So let's get underway. And I started by asking Harold to tell me a little bit about his background.
Well, I'm a carpenter by trade. My father was a carpenter. My grandfather was a carpenter. My great-grandfather was a jointer. So we were building in the building trades. And so when I was growing up, at about the age of 12, I was going with my father, and I was the gopher. Go for this, go for that. And so I learned building right from the bottom. And as I was going through high school, I was working every summer in the building trades. And when I started university, I actually contracted and built a house by myself for somebody else. And I got into engineering, and I was going to go into chemical engineering, but my marks weren't not the greatest. And so I went the next step to go to mechanical engineering. And I was at that time getting very interested in a girl. And, of course, that presents problems when she's 150 miles away. And so I wasn't getting my work done. And so the started the third year, and I dropped out because I was going to fail if I didn't. So we got married, and I was into carpenter work, and I did carpentry. And we were working on a 320-unit project in Regina. And I was working on this 320-unit project as a carpenter, and they worked me up until I was one of their most valuable employees. And I saw an opportunity then to go into architecture. So I applied for the job, got it, and worked then for almost 4 years as an architectural draftsman, working towards an architect degree. But the architect I was working under came to a situation where he didn't see the way I liked to see, and I didn't see the way he liked to see. And I thought there was time for a parting of the ways. So I applied to go to take architecture at the University of Manitoba. And architecture was a 5-year degree, and they would not accept any of the 2 years of engineering that I already had, not a single class. And I could go back to, since I had now a family with 2 children, I could go back to Saskatoon and complete my degree in 2 years. So we decided that was the thing to do. So we moved up to Saskatoon, went back into engineering, mechanical engineering, graduated in the top of my class, and the university suggested, you really need to go on and get a master's. Here's a man with a wife and 2 children, 3 children now, and I should go on to get another degree. So I did. Fortunately, I had a bursary from the National Research Council that paid some of my way. My wife was working. And I got in and took my degree, and my thesis work was I'd selected to work on air barriers.
Why?
Well, because basically at that time, if we were doing the calculations, engineering calculations on heat loss for houses, we could calculate the heat loss through the walls and through the ceiling and through the windows and the doors. But when it came to air leakage, you wet your finger and held it up and see which way the wind blew and grabbed a number out of the air. Literally, that's what you did. And you hoped you were in the right ballpark, because there wasn't any data on how to do this. So we worked on an instrument. I developed an instrument to measure, actually what it was measuring was the percentage of helium in air and a mixture of air-helium. And we were using helium then as a tracer gas. We'd put 100 cubic feet of helium in the house, and then we would measure and see how fast it disappeared. And we'd assume that the helium disappearing would disappear the same rate as the air. And this would give us our numbers. Unfortunately, that's an incorrect assumption. When you put a high concentration of helium in the space, the helium goes into closets and cupboards and spaces and so on. And so it artificially disappears from what you're emitting. So
extraordinary.
So it appears that it is the infiltration rate is very high, and then as the concentration gets down, the helium comes back out of the woodwork, and so now it's artificially low. And so what are you measuring? Well, you were measuring the concentration of helium, but that really doesn't do anything. So anyway, I got my second degree on that, and when I got my second degree, I went on staff at the National Research Council working on the same problem. And I just continued on for the next several years. And what we did eventually was then to change from helium as a tracer gas to sulfur hexafluoride as a tracer gas. And the advantage of the sulfur hexafluoride was we had a measurement system that we'd put it through a gas chromatograph, and the gas chromatograph would separate out the sulfur hexafluoride, and it would come through as a separate peak from the air. And so then we could measure the sulfur hexafluoride separately from the air peak. We knew what size the air peak was, and we now measure the sulfur hexafluoride peak. This would give us the concentration, and instead of using 100 cubic feet for a test, we could do the same test with 5 cubic centimeters, 1 teaspoonful. And so we're using very, very much less material to do our tests. And cost-wise, that was great. And the other thing was, since we're doing this, now we could use a constant concentration mode. We would pick a concentration that we wanted to say 15 parts per billion, and we would dump some sulfur hexafluoride in the space, measure it, and if it wasn't 15 parts per billion, we could calculate how much more we need to inject to make it, bring it up to that, and we just keep doing this every minute to take another measurement and keep measuring with a computer, one of the first computers that were available. And this worked very nice. But the problem was, in order to measure the infiltration in a house, we had equipment that today would be about $10 million worth of equipment. We had 2 men that were needed to put the equipment in the house and get it connected up and so on. That's at least half a day's work. And then somebody had to come into the house and monitor this every day for a week or a month or whatever period we're doing. And when we got that, then we could see what had happened in air change over the thing, and we could average it out or whatever you wanted to do with it. But it gave us the numbers. But it's not a practical system to do every house. You can't put this into every house and do it. And so our people in Ottawa were using pressurizing houses to see where how much air was leaking. And they had a very cumbersome system. They had about a 12-inch diameter duct, and it was 20 feet long. They put a fan on the end of it, and then they would go into the thing with a pitot tube and measure the pressure on a manometer in 10 equal spaces around the duct. And you have to precisely position this in each measurement. And I said, well, that's stupid, because it'd take you an hour to make one measurement. And you weren't even sure then. And if you're having to do 10 or 15 measurements to make, put on the graph so that you can calculate the infiltration rate, that wasn't appropriate. So I invented the blower door. And what we did was we took a piece of plywood that would fit a door, and we cut it in 3 equal parts, put piano hinges on it so they'd fold one over the other, and we mounted the fan in the center one. And now we had to measure the air going through the fan. Well, our people in agricultural engineering were using a smooth-edged orifice to measure this. And that was the logical thing. We put a smooth-edged orifice onto our fan, connect up a manometer to it, take one reading, and you got your airflow. And so that made it very, very much simpler. And so we started, had a company manufacturing nozzles, and Minneapolis Blower Door heard about it, read our paper on it, and came up to Saskatoon, bought some nozzles, went back to Minneapolis and started Minneapolis Blower Door. And so, okay, now we got tests. We ran tests on, put crews in and measured hundreds of houses for air leakage, because you can do it in about 15 minutes. And so now we have numbers of how fast the air is leaking in the house.
And which year is this?
I started my thesis work in 1960, and I started with National Research Council in 1962, and by the early 70s, we were the experts on measuring the leakage in housing. In the 70s, then, there was the Arab embargo on oil, because they thought they were getting not enough money for their oil. And so they shut down large oil fields and made a scarcity of oil. So overnight, the oil prices doubled. I mean, you went to fill up your car, and hey, instead of being 35 cents a gallon, it was 70 cents a gallon. And everybody was up in arms. And so you put half a tank of gas in, complained to your filling station attendant, and then went on to and then complained to the member of parliament about this. Well, the Saskatchewan government was really concerned about this, and they have a research arm. They've had a very active research arm called the Saskatchewan Research Council. And the Saskatchewan government asked the Saskatchewan Research Council to design and build a solar house appropriate for Saskatchewan. Now, the solar house, they didn't have any expertise at all in building, and so here they are. What do we do? Well, let's get a group of people together that know something about this. And so they called on me, because I was working with building research. They called on Bob Bezant and George Green and several other people from the university who were involved in building. And they asked people from HUDAC, the Housing and Urban Development Association, and from CMHC and so on. There was about 10 or 12 of us that were involved in this committee to get there. A couple of architects, and Henry Grohl, and a couple of architects sitting on the thing, and one student, Rob Dumont. And so we got together and we discussed the situation in terms of solar. Now, solar, first of all, there essentially is in our climate, there is no solar available between November and April. So if you're going to heat a house with solar, you're going to have to heat hot water in the summertime and store it for that. Now, if you take a conventional house, this requires about 3 Olympic swimming pools. And if you have 3 Olympic swimming pools, the evaporation from this will keep them cold. You have to have an awful lot of heat to try it. Your losses are 70%. You have to put in a lot more energy than you're going to ever get out. And so this just didn't make sense. And since we knew we did have energy available in the wintertime, what are we going to do? Well, we looked at it and said the logical thing was to simply reduce the energy consumption of the house to a very low value. So we sat down and started in and designed the house. And one of the first questions came up, well, how much insulation should we use in the walls? And somebody said, how about R20? And I said, well, the problem with R20 is that I know of several people who have built houses with R20, and I know that isn't enough. So my suggestion would be R40 in the walls, R60 in the roof. And I made the strong proposal that we do not put a basement in, because this house was to be built in Regina, and the number one problem with housing in Regina is basements. And at the time, they were recommending if you do have a basement, don't ever add insulation more than 2 feet below ground, because if you do, you'll freeze your footings and the whole thing will go to pot. And we're going to have to insulate everything, so we couldn't do this. So we won't put a basement in, we'll put it on pile and grade beam foundation. And so we then put... I recommended we put about R20 in the floor. We actually put in R30. So then the next problem was we knew that air leakage was going to be a major component. And at the time, there was nobody in the construction industry involved in making anything airtight. And I was the only one basically that had any knowledge on how to make things airtight. So I said, well, I will install the vapor barrier. So one of the technicians from the National Research Council and I went to Regina and installed the air barrier. And we did I think, not a perfect job, but a very good job for that time. And when the Saskatchewan Conservation House was built, it was the tightest house in the world at that time.
What was the air barrier?
The air barrier was 6 mil poly, and we used acoustical sealant to join one piece to the next piece, and to seal it as it went through the floor joists and the various things. And we achieved half an air change, 0.05 air changes per hour at 50 pascals.
Knowing what it's like today, that many buildings you'll go with the blower door, you'll test it, you'll address some of the issues. What was it like on this first house? Did you have to get that air tightness by going down the same route?
Well, I knew what we had to do, and so we went at it wall by wall, and the vapor barrier was on the inside. And we went wall to wall, and when we came to a partition, well, we had to deal with that. When we came to an electrical plug, we had to deal with that, and so on. And as a result of that, of course, we then switched dreams pretty quickly after we'd built the Saskatchewan Conservation House. There's better ways of putting the vapor barrier in than putting it on the inside. You put it in the middle of the wall, and you put it on the outside of the inside wall. This means that it's 3.5 inches from the idiots putting drywall on and all the other things. And you can go right past all the interior partitions. You can go past the floor joist. You can go past most things. It makes it so much sense. It's really simple to make a house airtight. You cut off everything on the outside that sticks out. You go to Mr. Glad and ask him to make you a garbage bag big enough for your house. You pick the house up, put it in, and you twist the top, and it's airtight. Now, the only problem with that is that now you've got your air and vapor barrier on the outside of the house, and you must keep this warm. So you have to put insulation on the outside of this. So our technique is, in the prairie double wall, is to make a light frame outside of the air barrier, vapor barrier, to make space for adequate insulation to keep the air and vapor barrier always above the dew point. If we do that, we have no problems. It's very simple, and if you do that, you can routinely make houses that are less than 0.1 air changes at 50 pascals.
At this time, you're creating a pioneering house. So what was the reaction?
Well, the house was built, and the government wanted to get the best exposure they had to it, so they used it as a demonstration house for 2 years. And essentially all of the students in high school in the whole province were bussed into Regina and taken through the house and shown the various features. We had 10 features basically on the house that they were looking at. We had the real simple one. To get the greatest volume with least amount of area is a sphere. The next one is a cube. And so the houses should be most volume for least area, because we want to reduce the area as much as possible. The next thing was we want as much wall for exposure to the south so that the sun can come in through the windows, so on the south exposure. So the house should be a rectangle with the wide side facing south. Those are sort of the logical basis that you always do. Now, the next thing they wanted to do was we had designed the house as a conserving house, but when we presented this to the government, they said, "Oh, that's very nicely done, but now we want it solar heated." Okay, so this is a slight change in plan. So in the far northwest corner of the house, we modified the plan just a little bit, and there's an 8-foot by 8-foot space that's 2 stories high. And in that 8-foot by 8-foot space, 2 stories high, is mounted water tanks, 6 feet in diameter and 18 feet high. It's insulated to R100. So we built the house, and the materials and labor for building the house was $60,000, approximately $60,000. And the materials and labor for building the solar system was $65,000. And we estimated that the house could be heated using 45 gallons of oil, 170 liters. And at the time, oil was less than $1 a gallon, so we could heat it for basically $45 for the winter. But we had the solar system. So anyway, they put the solar system on. The solar system had used vacuum tube collectors, very best we could buy. It had circulation pumps, it had temperature sensors, it had everything, heat exchangers to heat water from the solar system, to heat water for domestic hot water, to provide heating for the various things in the house. And this needs maintenance. And the first year, the maintenance cost was over $10,000 to provide the equivalent of $45 worth of heat with oil, and about $25 if we'd been using natural gas.
And this is something that they had pushed you into?
Yes, they pushed us into doing this. And the second year, the maintenance cost was not quite as high, but it still was up in the many thousands of dollars. So as soon as the house was sold, the new owner for the house, removed the solar system.
Well, you would.
Yeah. The other thing was, the big problem was nobody built triple glazed windows. And we needed at least triple glazed windows, and they're commonly available now, triple glazed, double low E, argon filled, on and on and on. But it wasn't available then, so we decided to put on shutters on the outside of the windows. Now, the south face had an overhang sufficiently long, and it was properly designed so that in the summertime no sun shines into the windows. In the wintertime, full sun shines in the windows, and the shutters were hinged at the top and would fold up against this overhang. But in the wintertime, when it's 40 below, the weather stripping on this is at 40 below, and it's like a piece of iron, and it does not seal. And so the cold air circulates around the shutter, and so, it warms up the windows a little bit, but we'd put something like R20 shutters on the thing, and they're more like R3. It's not very effective. So, guess what? The other problem is, with shutters, even though they're electrically operated, somebody had to go around and push the button for each shutter and make sure that the shutters were open in the morning and closed at night. And okay, that's fun the first day. It's less fun the second day, and after the first week, it's a pain. So they were never used. So okay, the next item was, well, we're going to recover all the heat or some of the heat from the gray water, and not having any experience on this, they came up with a counterflow heat exchanger that consists basically of a barrel where the gray water ran into, and then we took the gray water off the bottom over a weir and down the drain. So the barrel was always full. And then in the barrel we had a water coil, and the water coil then came in the bottom and out at the top, counterflow, because we're putting the gray water in at the top, goes out at the bottom. The fresh water comes in at the bottom, goes out at the top. Nobody had seriously thought about this, but after you have a shower or after you have washed your clothes, and there's water from both the shower and the laundry that was going into this, it has soap in it. And if you cool down the water that's washed from bath and has soap in it, it congeals. And so now you have a barrel full of jelly, and it doesn't work. So, okay. Scratch that one. Another thing that they did was they put an airlock entry at the front door and at the back door. Well, that's very important if your house is a sieve, and so the air, when you open the front door, it blows through the house and out the other side. But this is a very tight house. It doesn't do that. So the airlock entry is really very ineffective.
So some of these things that you were trying, was this house evolving, or was this all in one go? I'm slightly confused there.
Well, it was all in one go. But as a result of this, it gave us a lot of information as to how we shouldn't do things and how we should do things. And so the things that worked were the massive amounts of insulation, the airtightness, and thank goodness it really caused a revolution in the window manufacturing to make windows that are really effective. And windows that are, well, triple glazed, double OE, argon filled, windows even on the north side now gain enough energy through them to counteract their losses. They're heat gainers always.
How did you deal with the ventilation?
Oh, the ventilation, of course, was a concern. We recognized that we needed ventilation. So Dick Van E, from a technician at the University of Saskatchewan, was given the project of designing and building an air-to-air heat exchanger for the house. And he built the first one for the house. It was about 14 inches thick, about 2 feet wide, and it was 8 feet tall. And it used buoyancy effects because the airflow through it was quite slow, and the spaces were used 1/2-inch plywood to make spaces for it, and the heat exchange media was a sheet 6 mil poly. And so he designed it so that the cold air would come in at the bottom and go up through the heat exchanger. As it went up, it gained temperature, and it stratifies in the thing and goes up and comes out hot at the top, whereas the hot air comes in at the top, exhaust air comes in at the top and goes down. As it goes down, it cools, and at the bottom it goes out in the cold. So it's really quite effective. He built it in a couple of days in the shop at the university. It was installed, and it used fans from computer fans to provide the motive force for it. Very low energy use, and recovered high percentages of heat.
I think what's amazing me is how many elements of this you've managed to do on one project. I suppose it had to come together at one point, but there will be lots of challenges out there in the future, and people will need to come up with the ideas. So what advice do you give to people that are trying to solve what seem really difficult issues?
I think in terms of, if you take a look, and I don't care which program you use, PP or Hot 2000 or whatever, you should go ahead and analyze either the existing house you want to renovate or your new house that you're planning on designing, and put in whatever insulation you have or whatever you're planning on putting in, and look at the results as they come out, and it will tell you where the heat is going. You'll find in every case, I think without exception, the major component of heat loss is air leakage. And it really bothers me because I see so many people going out. Their siding is 30 years old now and it's looking decrepit. So they rip off the siding, they put 1.5 inches of styrofoam on and nail new siding on, and they think they're going to get a major reduction on their energy consumption. But they haven't done anything to do with air tightness.
Okay, well, let's look at that. You sussed all this out in the 70s. We're in 2015 now.
Yeah.
Why have we not progressed? I know, obviously, the passive house movement is taking hold, but why has it taken this long?
Well, in Canada, of course, the problem is that energy is still so inexpensive that it's still a small item on the budget. And
but this isn't going to look good in the future.
No.
When it runs out, the people who are living on the planet then will be thinking, what the heck were you doing?
That's right, exactly. And but it bothers me that to see people going in and ripping off their siding and putting 1.5 inches styrofoam and thinking you're going to get anything, because basically that reduces the heat loss through the wall, and the heat loss through the wall is normally around 10%. So if they double the insulation that was in the wall, they're going to save 5%, and I'll defy you to find that on your energy bill. But and people just don't recognize what happens. But to give you an example of this, a friend of mine in Saskatoon was trying to do all the right things. First of all, his furnace was failing, so he had to replace the furnace. So he went in and had the old furnace taken out, put a new high-efficiency condensing furnace in, and said, okay, I've done my part, okay. And then he looked up in the springtime, he happened to look up in his attic, and he found that they had blown about 6 inches of cellulose fiber over on top of the old insulation. And there'd been enough condensation because now with the new furnace, chimney is not active. Because the chimney's not active, this means that air comes into the house, it rises, as it warms up, it rises, tries to find its way out, and it goes through the ceiling into the attic space, but it has moisture. It condenses on the roof, and what had happened was he had 2 to 3 inches of frost up there. When it melted and came down, he now had 6 inches of wet paper mache in his attic. And he said, "What on earth do I do?" And I said, "Well, I'll tell you what the problem is. The problem is you've got holes in the ceiling where the partitions are, where the electrical boxes are, where the plumbing stack is. All of these are holes in the ceiling where the air is going from the house up into the attic, carrying the moisture there, where it condenses." And I said, "The only way I know of stopping that is to stop those holes. But unfortunately, there's no possible way of getting up there and doing it. You just can't do that." So he said, what do you suggest? And I said, "Well, I would suggest a chainsaw retrofit." And so...
Is this another one of yours? Is this another pilot? Oh,
yes.
My goodness. Okay.
So what we did was we had a bee with our church people, and they came over one Friday evening, and we stripped off the shingles off the roof. We got a chainsaw, and we cut the eaves and the overhangs off. We then made sure the roof surface was nice, no nails sticking up or anything, put polyethylene on it, put strapping on to provide 2x8s parallel to the roof edge, and then 2x4s on top. So we now have 12 inches of space. We put 12 inches of insulation on the top, a new roof deck and new shingles, and we got the roof done. We carried this down, and we took the siding off the house. We dug a backhoe and dug down to the footings. We carried the vapor barrier right to the footings. We started out with a foot of insulation at the footings and carried it right up to the roof. We put new exterior finish on. The house looks beautiful, and he's reduced his bill to practically nothing. He's essentially, if you would put solar collectors on the roof, he's a net zero house. And he has no more problems with condensation in his attic.
So that's your retrofit as well. You've had your new build and your retrofit.
That's right.
Well, it's been fantastic to get a chance to meet you and to have a chat. Maybe, is there one thing that you'd like to conclude this chat with?
Yes. If you're building new houses, build tight, ventilate right. If you're retrofitting, consider first, there's the first component of retrofitting, how am I going to make the house tight? Because that is the most important component. Make it tight, and then ventilate right.
Harold, thank you very much.
Okay, thank you.
As with all our podcasts, we provide online show notes. So today you can check them out at houseplanninghelp.com/95. You'll find a summary of our conversation. Also, you can take a look at some photos of the Saskatchewan Conservation House. And I thought for this episode, why not link to a number of other articles that have been written about this, because it is a famous project and he deserves a lot of respect. Thank you very much to Harold Orr for spending that time with us. houseplanninghelp.com/95. And if you have a comment, you can make it in the show notes as well. Just head right down to the bottom of that page. My call to action today, I thought I'd keep in line with what we've been discussing, which is airtightness, more or less. And if you haven't watched this already, last year we made a documentary called The Future of Housing and How Airtightness Can Help. The idea really being to try and give anyone the opportunity to understand some of these concepts that we've been talking about today. So you can discover why it's not just old housing that's leaky, why building regulations or code don't necessarily deliver you a high-performance, comfortable home. And this is within grasp as well. That's always crazy. This doesn't matter which country you're living in. I imagine the code is not up there at the same level as the Passive House Standard. And why the majority of homeowners are in the dark when it comes to these issues and how we could change things. So those are all things related to the documentary. houseplanninghelp.com/Future of Housing Overview. I'll embed it into today's show notes as well. Episode 95 is where we're at, so you can look at it that way if you choose to. Next time we move to New Zealand, and Dr. Cara Rosemeyer is my guest as we look at natural ventilation. Is it fit for purpose? The House Planning Help podcast is produced by Regen Media, content that matters.